Next, we're going to look at some training aspects of deep neural networks. How do we learn these networks? Okay, we're going to focus on two key techniques that are really enablers of deep learning: the gradient computation, specifically backpropagation, and computation and programming on top of the GPUs. Okay, without these, we wouldn't have deep learning. Okay, we'll also look at this technique of a dropout, which is not as common as the other two, but it's interesting in the sense that it has this aspect of changing the model during training, just for training, to avoid overfitting. So we're going to talk about that. Let us begin with backward propagation. So you need to remember that the way we optimize our loss function is through steps that are based on the computation of gradients of the coefficients, the weights that we have in our model, basically the weights that we fit when we train the model. Okay, and there are different ways of doing that. Like, are we using all of the examples to compute the gradients? Just one random example, like in SGD, a few random examples, mini batch, stochastic GD, or we do it on the entire data set, splitting it into batches, and then when we are done with all of the batches, that's an epoch, and we can run several epochs. So different techniques based on different ways we use the data in our training. And then there's a question of what do we do once we have the gradients? You can apply a constant reaction, basically update, like in plain gradient descent, or techniques that adapt through time, like the Adam optimizer. But in the end, all of them are based on gradient computations of derivatives. Okay? And if you're not careful to do it efficiently, you can be in trouble because there are lots of gradients. There are lots of parameters. Think that, whenever you have a linear layer, you have a matrix, and all of the entries of this matrix are parameters. So there are many parameters, many gradients that you need to compute. And the interaction between the gradients can be complex. We'll see that it's not that complex, but it can be complex because, one is built on top of each other. So how do we compute these gradients? This is what we do in backward propagation. It's an efficient technique for computing these gradients, basically in two passes over the network: forward over the layers and backward, from the output to the input, from the input to the output forward, from the output to the input backward. Okay, no further communication between the layers. Okay, now this is what you need to remember: each layer is basically responsible for computing the derivatives, okay, the gradients of the parameters of it, the parameters that this layer introduces, and also deliver whatever information, basically multiplier, that the layer underneath needs to compute its own derivatives. Okay, now this is a very useful as a programming paradigm, because think that, if you have a machine learning library and you want to introduce a new unit, you don't need to change everything to now compute gradients that include this new unit. All you need to do is to say how this new unit computes its own gradients, the gradients of its own parameters, and what it needs to deliver to the layer underneath. Okay? Now, our description will focus on feed-forward networks, okay? Simply because recurrent networks are more complex, because we are reusing parameters, you're doing parameter sharing, so you need more complex techniques like backpropagation through time, but the idea is similar, okay? So this is how it looks like, okay? Two passes in backward propagation, forward and backward. In forward, we basically compute the loss. This is the blue lines. Here we compute the loss. In the current, with respect to the current weights, okay, of the parameters, of the current values of the parameters. And in the backward step, we actually compute the derivatives. Okay? So here, for example, z is a function of x and y, and we want to compute the derivative of the loss function with respect to x and y. So we say, okay, this layer knows only z. So we'll compute the derivative of the L with respect to z, which is hxy. And then we'll send this value back. When you want to compute the derivative of x with respect to L, you need to multiply what you got here, derivative of L with z with respect to L, um, by the derivative of x with respect to z. Same here. You want to compute the derivative of y with respect to L, use what you got previously, multiply it by the derivative of y with respect to z. That's the idea. That's the basic chain rule of derivative, and we're going to use that. Okay, so slightly more formally, a forward pass evaluates all of the units in order, all the way to the loss function. The parameters that we use in the uppermost layer, like softmax or something like that, all we need for that, if you think of it, is the result of the previous layer. We don't need anything other than that in order to compute the gradients of the parameters of the uppermost layer. But what happens to the parameters in the lower layers? So for the lower layers, the gradient is basically a product of a constant that we can compute in the uppermost layer and derivatives that we can compute just in the lower levels, okay, lower layers. Okay, therefore, each layer passes this multiplier, the thing that we need to multiply with, to the lower layer, and lets that layer take over. And you continue with that backward all the way to the input, and therefore you cover all of your parameters, compute all of their derivatives, and then you can do whatever you want, gradient descent or a Adam optimizer, whatever.